Okay, so where we've been, what we did, exact rate of change we started with, is that right? And from that we created approximate rate of change using r of left of x or r of right of x. It's a step function that tried to pretend to be that rate of change function. And then from that we built up an approximate accumulation function. That was our piecewise linear function based on those constant rates. And delta y equals k delta x. And then from that, we let delta x get very small. And that led us to the exact accumulation function. So that was what we've been working on for the last month or 6 weeks. So now, and then what we said was, since we did all the groundwork, we paid our dues. We could just give an exact rate of change. We could write down what the exact accumulation function was with an integral, right? An integral allowed us to write down what exact accumulation was directly from exact rate. Okay? So now we're going to change it around. So now we have an exact accumulation. We're going to build an approximate accumulation function. And from that approximate accumulation function, we're going to gather our approximate rates of change. And then we're going to determine an exact rate of change function from that. Okay, make sense? So we're going to turn the whole process around. But because we've done all the hard work in the middle, we don't have to redo. This is going to be a lot faster to get to understand this, get through it, because we don't have to establish all these bits and pieces that it took to get from exact rate to exact accumulation. So we can just use them. Now we can just use them, and this will be a faster process. Okay, and then the end goal is exact accumulation to exact rate in one step. Okay, so where do we find exact accumulation functions? Where in the world do we find exact accumulation functions? What are those? Yeah, the integrals of the rate, true, but now we're starting with an accumulation. So in the reverse journey, we're going to start with accumulation function, right? We're not going to build it from rate. We're going to start. So where does an accumulation function come from? Okay, so you've been dealing with these your whole math career. It's any quantity function. Any quantity function we can think of as an accumulation function. So, for instance, area of a square, right, equals x squared. That's an accumulation function because we can think about the area accumulating bit by bit. Okay, so the area of a square with side length 3 is 9, and we can think about that amount 9 square inches or whatever it is having been accumulated from 0 square inches. Okay, so any quantity function can be thought of as an accumulation function. Okay, and as such, then we know that it also can be thought of as the integral of some rate, right? Sphere, okay, so the volume of a sphere. Volume of a sphere is another example of a quantity function, which we can think of as an accumulation function. And so therefore, it's the integral of some rate. It's the integral of some rate. So the question is, given that volume function, what is the rate? So that's our new question. Given the volume question, given the volume accumulation function, how do we determine what its rate of change is? Which would be the opposite situation of what we've done. Okay? So we're going to devise a way to figure that out. Okay, so there's one important kind of key element to this reverse process that we haven't talked about yet. So that's what we're going to talk about today. So to start talking about that, we can start with Usain Bolt. German. and the cameraman running after him. Okay, so Usain Bolt, he ran the fastest ever 100 meters. Okay, he ran the fastest ever 100 meters. I think that was in Beijing. Was that in Beijing? The World Championships? In Berlin. Therefore, the German. Okay, so he ran 100 meters in 9.58 seconds, which is the record that still holds today. Okay, so he ran 100 meters in 9.58 seconds. How fast did he run? How fast did he run? Can you figure it out? How fast did Usain Bolt run? If he ran 100 meters in 9.58 seconds, how fast did he run? What's that? He said 10.43 meters per second. Someone else get that? How would you figure that out? How fast did he run? Take his meters divided by his seconds. 10.44. So, what does that have to do with his race? How can you interpret that number? How do you interpret that number, his speed? How do you interpret it? Tell me that you raised your hand in the back. How do you interpret that number? Yeah, no, how do you interpret it? So what does that mean, 10.44 meters? You go 10.44 meters every second. Okay? Agree? So did Usain Bolt run 10.44 meters every second in his race? Oh, some people are saying no.
That's just the average.
Well, that's the average. So he didn't do that. He didn't run 10.44 meters every second. What about in the first second? Did he run more or less meters than that?
Less.
He ran less, okay? So because he has to start from a zero speed, right? So at the beginning, he's covering less distance per unit time. Okay? And then did he ever run faster than that? Did he run more than 10.44 meters in a second? He must have, right? He must have. Okay, so then what is this thing, the average speed? What does that mean? Is it like you add up all the speeds and divide by the number, like your test scores, like your average test score? Is that what this is about? No, it's not. Taylor?
That is the speed it would take for another person to travel the same distance that Usain Bolt traveled in the amount of time that he traveled.
Okay. So he's saying it's the speed someone else would have to travel to cover the same distance in the same time. Yeah.
Well, yeah, it's the constant speed someone would have to invent in order to travel that same distance in the same time.
It's only one number, right? How many speeds did Usain Bolt run in the race? Many, many, like an infinite number, right? Starting at 0 up to faster than this, right? So he ran at any given moment, he's running many, many, many speeds. But when you calculate the speed this way, you get one number. And so if it's one number, then what do you think? He's saying it's a constant speed. Would you agree? Yeah, exactly. So it's the constant speed. Like they said, this is the constant speed for Usain Bolt to cover the same amount of distance, which was how far? 100 meters in the same amount of time. So I recreated this. With graph and calculator. So I used graph and calculator to recreate his race. So there's a 3-second countdown, and then he goes. And this simulates how he moved along in the race, and there's 9.58 seconds. Okay, so 3, 2, 1, go. So I want you to talk to the person next to you and explain practice explaining. What does the number 9, so we calculated his average speed as 9.44, 10.44 meters per second. What does that number mean relative to his race. Practice explaining that. What does that number mean relative to the race that Usain Bolt ran? Go.
It shows what it looks like when something is actually traveling 10.44 meters every second in an interval.
Okay. So she's saying that Emma is actually doing a constant speed of 10.44 meters per second. Is that right? Right, because she travels the same distance in the same time. So somebody else, what does that have to do then with Usain Bolt? Yeah.
Does it show the difference of how he is not going a constant of 10.44, but at the very end is?
Same distance, same time, right? Same distance, same time. So Emma is representing what? What does Emma represent? Does she represent? She is running a constant rate of change, but what does she represent? Usain's average speed. You see, the point of Emma is to show Usain's average speed, the constant speed needed to go the same distance in the same amount of time. So average speed is like, it's not adding up a bunch of things and dividing by the number of things like you average your test scores, right? It's like another situation, a parallel situation where you have constant speed such that you cover the same distance in the same time. So Emma represents the average speed of Usain. Okay. Any questions on that? Okay, when they get to the ends, pass them up and down. Right. Okay, so I've got this another graph calculator file. Okay, I'm showing I've created a glass here, like a standard glass for water. Okay, and so this is view 0. So you got some questions there for view 0. So go through those questions and we'll recap in a minute or two. Okay, so work through the questions. This is view 0. Well, let me read the setup. Okay, so consider a typical bar glass being filled with water. We're going to investigate how the following two quantities change together: the number of ounces of water in the glass and the height of water in the glass in inches. Okay, so you're doing the first 3 questions. View 0. Go. Number 2 is the most important question in the first 3. Number 2. Sorry I didn't leave enough room, but do your best. Extra sheets. Okay, we'll make one round. You got questions? Stop me if you got a question. Yeah, just use 0. Just the first 3 questions.
Yeah. I would just take this volume. Okay. Yeah, so what more specifically than that? So how does the increase, say, for equal volumes, so how would it be equal 0 to equal volumes, how would it affect? Yeah. More specifically, goals. So for question 2, you would consider equal volumes of water added the whole way across. And so you want to be specific about more than just, the height increases, right? The height increases as the volume increases, that's true. But for specific, for equal increases in volume, can you be more specific about the changes in height that result for the filling of the whole glass? Okay, does that make sense? So question 2 is more than just the height increases as the volume increases. I want more specifically. How does it increase? How does it increase? So for number 3, you could make a little sketch of what you think the graph will look like. Over to the right there, there's a little space. Sketch what you think the graph will look like for number 3. Okay, so let's see how you did. So hopefully the first question was easy. What's the input quantity based on the axes? Volume of water. Okay, output, height of the water. Okay, so how does the height of the water change with respect to the volume of water increasing? So specifically, how does it do it? Scott? For equal increases in volume, there'll be decreasing increases in height. If that makes sense.
He said for equal increases in volume, there will be decreasing increases in height. What do you think about that? So at the beginning, what are the changes in height like? For equal changes in volume at the beginning, what are the changes in height like? Bigger or smaller? Larger because? It's narrow. The glass is narrower, so the same change in volume is going to result in a bigger change in height. Is that right? And then as we fill the glass towards the end, the same changes in volume will result in what kind of changes in height? Smaller changes in height. So then, if you can imagine then, what will that graph look like? With those changes in height decreasing, right? They're increasing height, but those changes are decreasing. So draw it with your finger. Okay, so that's the graph. That's the graph of height of water versus height of water with respect to the volume of water. Okay, any questions so far? Okay, you got a couple questions for view 1. Okay. Question 5, the most important of these two. So numbers 4 and 5 for view 1. Question 5, the most important. Just to remind you, neither of these quantities are time, okay? It's not about time. So keep focused on these two quantities, height of the water and volume of the water. It's not about time. I can take water out of the glass, okay? I can take water out of the glass and the height can decrease, so it's not about time. Oh, you actually got, sorry, you got 3 questions. You got 3 questions for this. What'd you get for the average rate of change? Let's write it down. What'd you get? Anyone get the number? Yell it out. 0.361? And what are the units on that number that you calculated? What's that? I have inches per ounce. Agree with that? Or is it ounces per inch or something else? Inches per ounce. Okay, so now we want to interpret. Number 5. Most important thing. How can you make sense of that number, 0.361 inches per ounce? What does it mean, that number? Is it George? No.
No, David.
David. George over here.
A 14-ounce glass with sides perpendicular to the table that it's on top of and 5.052 inches tall would fill at this rate.
Okay? Did you hear what he said? Say it louder, one more time.
A 14-ounce glass with sides perpendicular to the ground and 5.052 inches tall would fill at this rate.
Agree with that? So he's talking about another glass. He's talking about another glass that has What kind of sides? Straight sides. How much water fits in that glass? Same amount. Okay? And how tall is it? Okay? So it's just a single number, which means it's what kind of rate? What kind of rate of change? It's a constant rate of change, right? It's a constant rate of change. So, and then what about the graph? So what is the red graph showing? The constant rate. What constant rate is it showing? Someone say. Someone say. The what? Okay. So do you mean this one? Maybe? Maybe? Is that what you meant? Okay. So we're all the way to view 3 now. David just catapulted us forward. Okay, so view 3, answer question 7, and the recap. So see if you can come up with a definition of average rate of change on your own after answering question 7. So how does this animation give us a way to think about average rate of change? Somebody new. How does this give us a way to think about average rate of change? Moises, want to give it a shot?
It allows us to see 2 different situations in which the same thing has happened in 2 different ways or rates of change.
Okay. But how is it illustrating average rate? So which is our focal glass? The first one or the second one? What's the glass of focus here? First or the second? First. The first. So what is the second showing us about the first glass? So the second glass is to aid us in our analysis of the first glass. The second glass is to aid us in our analysis of what's going on in the first glass. How does it do that? What's that? She said, you're saying this is showing the average of this one. Is that what you're saying? She's saying this shows the average rate of change of this glass. Does that agree with that? That's right. That's right. Because the average rate of change would be what? The constant rate that would result in? Would result in what? The same height for? Same amount of water, right? So so it's the constant rate of change, in this case, that would result in the same height of water for the same amount of water. That's the average rate of change of the first glass. So let's just summarize that here. Okay, so average rate of change is the constant rate. Stop it. Quick. Made it. So it's the constant rate that what? Produces the same height. That's our change in height, right? Filling up the glass. For the same for the given change in volume. Okay? Average rate of change, the constant rate that will get the same change in height for the given change in volume. Okay, flip it over. Let's try this one. Okay, so now what I'm interested in is let's go right to view 1 here. I'm interested in a change in volume of 5 ounces starting when the glass has 1 ounce. Okay? So we want to consider the change in volume when the glass starts, starting at 1 ounce, when the glass has 1 ounce, ending at 5 ounces. We want to find the average rate of change of water height with respect to volume. Can you do it? Does the question make sense? So now I don't want the average rate of change for the whole glass being full, just for this change in volume, starting at 1, for a change of 5 ounces. Can you find that value? Tell me.
Can it be done without knowing the change in, I guess, height as well? Or I mean, yes, change in height.
He thinks he needs to know the change in height.
How do you know what the height was at 1 and the height at 5?
He wants to know the height at 1 and then the height at what? At 6? What do you think? You need that? Yeah. So you either need the function rule for this graph, or I can just pick it off for you. Ready? So here we go. At 1, the water height is 0.543 inches. I think he's on to something, right? I think he's on to something. And then at 6, the water height is 2.66. So 0.54 and 2.66. Now can you find it? Find the average rate of change for this particular change in volume. And then answer number 3 as well. So what would you add visually to this graph to demonstrate that new average rate of change that you're finding? What visual elements would you add to this graph to demonstrate that number of average rate of change that you just found? Make a sketch. Do we have a value? What do we get for this particular average rate of change?
0.4234 inches per ounce.
I heard 0.4 something.
0.4234.
23423. And he wants inches per ounce again. Agree with that? And so what would we add to demonstrate that value? What would we add to the picture to display that or demonstrate that? Yeah?
You could have the actual change in height.
Okay.
On the left, and then you would be able to calculate change in height or change in volume, and then you would have a constant linear line connecting the 2 points.
So he wants to show that corresponding change in height over here, and then he wants a linear graph connecting the starting and ending points on our graph. Agree? You guys are all ahead of me today. Exactly. So there it is. So there's the corresponding change in height, and then the purple straight line is showing the average rate of change for that change in volume. Okay? So how does that average rate compare with the average rate for the whole glass that we found before? How does that average rate of change compare to the average rate over the whole glass that we found before? Yeah.
It's closer to the actual graph.
Okay, it's closer to the actual graph, that's true. But just comparing those two average rates. So the purple is showing the new average rate for the change in volume from 1 to 6, and the red graph is showing the average rate for the whole filling of the. Comparing those two, what could you say? Yeah.
Greater.
It's great. Which is greater?
The smaller one is greater at that point.
Yeah, we got a higher constant rate, right? And so how does that show up in the graph? The fact that we got a higher constant rate. Yeah, so for changes in volume, you get more of a change in height. Okay, so its slope is greater. Okay? So, how could we then, thinking about how we represented the red graph with another glass, what would the glass be like that represents this purple? So imagine, what would the glass be like that would represent this new average rate of change, the purple one? Talk to the person next to you. So we know what the red one was, right? So what kind of glass would you need to represent the average rate for this new change in volume? Tell the person next to you. Go. So what about that glass? So it's going to start now at the 1 ounce level, right? And only go up, or the 1 ounce, the height at 1 ounces, and then whatever that second height you had was. And then it will be, what's skinnier, right? Because there's a higher average rate. So for the same amount of volume, you're going to get, at a constant rate, you're going to get greater changes in height. Okay, so what's the definition? What's the definition of average rate of change? Now for any two quantities. So we have any input quantity, any output quantity. Can you write a definition for average rate of change? Any input and any output. That's the bottom, the summary. See if you can do it. Any input, any output. What's average rate of change? So here's how I'm going to start it. Given a function and a specified interval of input, the average rate of change over this interval is what? So given a function and a specified interval of input, for instance here, this change in volume, the average rate of change over the interval is, who could give me something? Good. First and foremost, average rate of change is That's how you calculate it. That's how you calculate it. So that's true. But I'm looking for, nope. I'm looking for what is average rate of change. What is it? What does it mean? Adam, was that a hand? Too close to a hand. Sorry, go for it.
Okay. Average rate of change of that one interval or
First and foremost, what is it? First and foremost. What's that?
Is it constant?
Constant what? Constant rate of change. The average rate of change, first and foremost, is a constant rate of change. Which constant rate of change is it? In terms of the input and the output.
It's constant rate of change in the output.
Yeah, but it's the constant rate of change that does what relative to input and output? Yeah.
The constant rate of change that it would take to reach, travel the same distance and, gain the same increase of the quantity.
Output.
The output in terms of the same amount of input.
That's right. She said it's the constant rate of change that's going to realize the same what? Change in output for the given change in input. So that's what we're trying to talk about all class long. Constant rate of change that yields the same change in output as the function over the same interval of input. So in terms of this backward journey, we have accumulation like this. This is an accumulation function, accumulation of height. And we're trying to find the rate. This idea of average rate of change is critically important. Okay, the constant rate of change that yields the same change in output for this given change in input. Have a great weekend. Everyone who showed up you'll get a full credit on a homework assignment. Okay.